Alright, so finally let's talk about the error propagation algorithm, which is a very important algorithm you should understand and also follow. So please make sure be careful when you are checking the following pages of the lecture and also when you are reading the textbook and the reading materials. Make sure you can follow this error propagation algorithm very well because it is so important. Okay, so here we will take this MLP model as an example to introduce this error propagation algorithm to you. So before we have defined one MLP model, right? And we also try to define a loss function of this model based on some training data set. So for this MLP model, given the input, we can define its output as well as hidden neuron representations, right? By the formula we show here. We introduce some intermediate results, by this alpha H for neuron BH, right? And we can further, based on this intermediate result as well as threshold, we can define its output. Similarly, for the output neurons, we also define this beta J as an intermediate result, right? And based on it, as well as threshold theta J, we can further define the output. And we also define the loss function as we are seeing at the bottom based on the square arrow, right? Then let's talk about how to train the model. So the training is still based on gradient descent. It is still based on gradient descent. How can we train the model? Right, so because we have so many different parameters in the model architecture, we have both W, theta, we have V, and gamma here. These are all the parameters to be learned by the model. Then you remember, how do we define the error function or the loss function? We define the loss function based on the output from the output layer, right? In other words, the errors or the loss function is more close to the output layers than its hidden layers. So therefore, let's take a look at the output layer first, and how can we learn the parameters for both theta j as well as w, these parameters here, as shown here. So the first step, we still need to calculate the gradient, right? If you still remember, we need to calculate the gradient of the loss function versus the parameters. Let's take a look at the gradient of w parameters first. So we define the gradient of this loss function versus this parameters w as shown here by this formula. We have the partial whj denoting the loss function, denoting the partial derivative of the loss function versus its whj, its parameter. We denoting the term as partial whj. So here for the gradient term, we have this negative mark. We move the negative mark from the gradient descent, this formula, into its gradient. If you still remember, when we talk about the gradient descent, we mentioned that for updating the parameters, we have like a w equals to w minus some terms, right? But here we put this minus into the gradient instead. Therefore, when we are updating the parameters, we have plus here instead, right? And we put this negative or the minus into the gradient, as shown here. So by calculating the partial derivative of the loss term versus the parameters, remember when we are calculating the partial derivative, we have to utilize the chain rule, right? Because this EI is defined by the y hat. This y hat is defined by this f together with beta j, right? And this beta j is defined by this w here, right? In other words, if we want to calculate the partial derivative of this EI loss function versus this whj, we have to calculate what? We have to calculate the partial derivative of this loss function versus y hat first, right? Yij hat first, right? And then further calculate what? Then we can further calculate this y hat versus beta. Then further calculate the partial derivative of this beta versus this parameter, right? By the chain rule. Okay, so first let's take a look at the first term, the partial derivative of this loss function versus y hat. Let's take a look at this loss function first. This loss function equals to the square arrow of this y hat, minus this ground truth. The ground truth is a constant, right? Therefore, if we calculate the partial derivative of this EI versus y hat equals to what? It equals to this y hat minus this ground truth, right? And let's take a look at the second term, the partial derivative of this y hat versus beta. This y hat equals to what? Equals to the activation function of the beta, right? If you still remember, we have defined different activation functions. Here, if we use sigmoid function, we mentioned that the partial derivative of the sigmoid function versus input equals to what? If you still remember, right, for sigmoid function, its partial derivative equals to what? Equals to fx times 1 minus fx, right? So here, therefore, For the partial derivative of this y versus beta, it equals to what? It equals to fx times 1 minus fx, right? Here the fx equals to what? It equals to y hat, right? You can follow me, right? So this is a good property we can use for the activation function into the learning, right? Okay, so this is the second term, and then let's look at the third term, the partial derivative of the beta versus the parameter. If we calculate the partial derivative of the beta versus parameter, it equals to what? We have beta equals to the weighted summation of the parameter times the BH. BH denoting the representation, denoting the output of the neurons of the hidden layers, right? If we calculate the partial derivative of the beta j versus w, it equals to what? It equals to BH, right? You can follow me, right? So you can see, according to the chain rule, we can calculate the partial derivative of all these terms inside it very well, very effectively. This one is according to a loss function. We use the square arrows. It equals to y hat minus ground truth. So for the second term, we just utilize the second function derivative. It equals to y hat times 1 minus y hat. For the third one, it's just a weighted summation. If we calculate the partial derivative, it equals to the BH, right? So you can follow me, right? Then actually we can introduce one more term. We define one term. It's called GI. We define GI as what? We define the GI as the negative partial derivative of the loss function versus y hat times partial derivative of y hat versus beta. In other words, we define this term to be an intermediate term GI. You can follow me, right? Then we can have GI equals to this term. According to the above calculation, we have this term equals to what? Equals to y hat minus y, the ground truth, times y hat times 1 minus y hat. You can see what? You can see that GI equals to what? In other words, we can directly calculate the GI according to either the ground truth or the output values by the neuron, right? Because we have the y hat to be the output by the neuron, right? So before we do the learning, we know the output for the neurons already, right? Because we have the input, we can generate the output. So this GI can be directly calculated by the output as well as the ground truth. You can see right here we have one negative mark. However, in the result, we have no negative mark. The main reason is because we switch the position. Originally, we have partial derivative of EI versus y hat equals to y hat minus y, right? This is ground truth. If we move this minus into this term, we can have y minus y hat instead for the GI definition. So by this GI, which can be directly calculated by both ground truth as well as output of neurons, and by this GI, combine this GI with the remaining term, we can define the partial derivative of this parameter w to be what? To be GI times BH. So you can follow me, right? So this GI is something related to what? Related to the output layer, either the ground truth or the output layer representation. This BH is what? This BH is the output of the hidden neuron, right? In other words, the gradient of the parameters connecting the hidden neuron to the output can be directly calculated by both the hidden neuron output or the final output, right? They can be directly calculated by the GI times BH. So the GI can be so useful because in the following page, we'll show you that we can use this GI again in the following layer updating. So far you can follow me, right? We have calculated the partial derivative of this loss function versus W parameter again in this page. By the chain rule, we can calculate each term inside it, and we define one intermediate result, GI here. Then we can represent this partial derivative to be GI times BH, right? Inside it, we will use many of the properties for both loss function, for the activation function, as well as for the weighted summation here, right? So according to the gradient we calculate here, we can further update this W, right? According to the gradient descent algorithm, we can update this WHJ to be the parameter in the previous round plus eta times the partial derivative of the gradient, right? Here we have a plus because we move the minus inside this term instead, right? And here this partial derivative equals to GI times BH. Okay, so this is for the W. How about the theta? We can do the learning of the theta in a similar way, right? To be theta j equal to theta j plus eta times a partial derivative of theta j of loss function versus the parameter is theta j here, right? And an interesting part here is that the partial derivative of theta j actually equals to the negative gj. This term we defined before. In other words, once we calculate the gj for updating this w, then when we're updating this theta, we don't need to calculate the gj again because we can directly use this gj directly to update this theta j, right? So you can see we can utilize this intermediate results we defined above in the updating of the other parameters. We don't need to recalculate this gj over and over again according to the chain rule. So this error propagation allows us to utilize some of the intermediate calculation results for the parameter updating. Now here we have the gj calculated for the w, then we can utilize this intermediate result for updating theta as well. Okay, so this is for the output neurons. We have updating this w and theta here. Then how about this v as well as gamma we show here for these parameters? We can do the learning in a very similar way according to the gradient descent. And we also utilize the chain rule. We derive the chain rule first and to see their correlations. Now for the VIH between the neuron, like I is input neuron with this BH, this is a hidden neuron. We can update the parameter V as a VIH equals to VIH plus eta times partial derivative of VIH. And here we also have a very interesting observation. Because according to the chain rule, we can calculate this on our paper. And we find that this term can be represented as what? It can be represented as a product of EH times XI. XI is the input, we have nothing to say, right? How about this EH? This EH is another intermediate result we define for the hidden layer. This EH equals to what? It equals to the negative because we move this minus for the gradient descent into the partial derivative, right? We have the negative partial derivative of loss function versus BH. And then we have times it with this partial derivative of this BH versus alpha H. What is BH? BH is the output for the hidden neurons. How about this alpha H? Alpha H is the intermediate result we calculated for the weighted summation, right? From the inputs. Then according to these kinds of terms, we can calculate this partial derivative of E versus B as what? So we can calculate this partial derivative of loss function versus BH as what? Because this loss function is defined based on y hat, right? And the y hat is defined based on beta, and beta is defined based on b, right? Therefore, according to the chain rule, we have to do the many of steps, and we can represent the result to be what? It will be equal to the summation of all the output neurons. We calculate the partial derivative of loss term versus all the intermediate result for all the neurons, and further times its product versus the BH. And here we also need to calculate this term, right? Partial derivative of this BH versus alpha H. This can be defined by the activation function we are using here, right? And then we can further simplify its representation. First, this term, right? The activation function partial derivative. If we use the sigma function, we can represent this term equals to what? Equals to BH times 1 minus BH, right? It is so simple. How about this internal side, this term? So we can simplify this term to be what? To be the summation of the weighted summation of GI. You can see a very interesting part here, right? So this BH times 1 minus BH is about the hidden neurons. This GI is about what? This GI is something we define from the previous term, right? The GI is what we define here. However, this GI can be further reused for defining the EH term, right? This GI quantifies the errors we make for the output layer. However, when we are updating the hidden layers, we can still utilizing the errors we define for the output layers to update its parameters. In other words, we can backpropagate the errors we make from output layer to the hidden layers for updating its parameters. Right? We can reutilize this GJ again we defined before for updating all the hidden neurons. So you can see, right? For the error propagation algorithm, this term we defined before for the output layer quantifies generally the errors we make, right, compared with the ground truth. And we will backpropagate this GJ term to the hidden neurons to define this EH. Right? This EH defines what? This EH quantifies something like the errors we make for the hidden neurons again, right? And so according to this EH representation, we can update the parameters VIH as shown by this formula we show here, and we have this learning rates to be eta as shown here. Besides the VIH, we can also learn this gamma H for the neuron in the hidden layer as well, to be gamma H plus eta times a partial derivative of its gamma H, right? And an interesting observation is that it's a partial derivative of loss function versus gamma H equals to what? Equals to negative EH again. So in other words, we just need to calculate this EH one time, and it can be reutilized again for updating other parameters. So you can see, when we do the learning inside the MLP, before we have the gradient descent algorithm, right? You can calculate the loss function, to all the parameters according to the formula we showed before, right? One by one. This is one way to do the training. However, we find that actually when we apply the gradient descent algorithm to train deep learning models, so many of these intermediate calculation results can be reused. Like GJ here. We use this GJ so many times, here, here, and here, right? Similar for this EH, this intermediate result we define here can also be reused again for updating many of the parameters, like here and here. And if we have even deeper layers, then this EH GJ can be further reused in the following layers. Right? So you can see we can reutilize many of these intermediate calculation results for updating the parameters. And these intermediate results actually quantify somewhat like the errors we make from the previous layers. And we can utilize the previous layer errors back into the current layer updating. This is the reason why this algorithm is called the error propagation algorithm for updating these parameters. So you can see, right, how this algorithm works and what's the difference of this algorithm compared with the traditional gradient descent algorithm. Okay, so I hope I can make it clear for you how do we do the learning. And by these formulas we show here, then we can do the updating of these variables, parameters one by one, according to the formula we show here, right? And also layer by layer. Okay, so this is a very important error propagation algorithm we have to mention here. You can see it is defined based on the gradient descent algorithm. However, inside it, we define some intermediate result terms, and then we can utilize these terms for speed up many of the calculation process, because we can reutilize many of these intermediate terms for updating the parameters, which can speed up the learning process. I hope you can follow me right. So please check these pages very carefully to make sure you can follow my ideas and also follow what we are doing for this example. And generally, the error propagation will be used in almost all the deep learning models nowadays, as well as in your project. And when you are writing your code, you don't need to define this error propagation process, because this process can be defined by the PyTorch automatically by itself. You just need to define your model architecture, and also you define your optimizers and some parameters. Then this error propagation can be done by PyTorch itself. Okay, so this is about this section. We can do a very quick summary. So in this section, we discuss what is deep learning and why we need to have deep learning. We will provide you with a brief history about deep learning and what makes deep learning work. And we'll cover some basic technical details about biological neuron as well as artificial neurons. And we discuss the perception and its weakness, and further discuss about multilinear perception and applications. And finally, we'll talk about how to train an MLP, and we talk about the error propagation algorithm, which is a very important algorithm for us to use in deep learning. And we have some after-class tasks for you to do. First, for the readings, please read the corresponding chapters of the textbook, and also please read the section 2.6 on neural nets in the Machine Learning Basics article. And also we have some optional reading assignments if you have time. And also if you are interested in the structure as well as the biological function of the brain, you may refer to the brain tutorial 1 and tutorial 2 for your information after class. If you don't have time, then you don't need to read them because they are so long actually. For the project, we will move to the stage 2, and please check the MLP code we provide in the stage 1 in the code template. Make sure you can understand the code organization as well as the contents in the code. And please also download the dataset for stage 2 and check the dataset contents and formats. Try to implement your own MLP model and also evaluate its performance. And write your report with your teammates for stage 2 based on provided report template. We will have the report to be due by the midnight of Friday on January 28th. And we also released the homework 1 with 5 questions in the schedule spreadsheet, and you can start to work on some of them now. And it will be due by the Friday midnight of February 4th. It is still several weeks away. You don't need to rush actually. Okay, so that's it for this section, and thank you a lot for your attention.